Hello. In this chapter, you are going to learn the development, the meaning, and the uses of the periodic table. The known elements were already being classified according to their properties or their atomic masses in groups of 3 or groups of 7 by certain scientists. But only in 1869, Mendeleev came up with the idea of repeating order of atomic properties when the elements were arranged in the order of increasing atomic mass. His idea was to arrange a periodic table in columns by putting the elements with similar formulas of their oxides in the same columns. For example, he put the elements lithium, sodium, potassium, and hydrogen, of course, that have a formula with oxygen R2O. If the formula was RO, for example, 1-to-1 ratio, the elements fell into that category were beryllium, magnesium, calcium, etc. So according to the formula of the compounds they form with oxygen, Mendeleev put his elements in columns. This was a genius way to begin with because there were, of course, some missing elements. For example, the ones that are showing as Eka, means coming after, were unknown by Mendeleev. But what Mendeleev did was to predict the properties of these unknown elements, and he predicted them with pretty good accuracy when the elements were actually discovered well after Mendeleev's passing away. The observed properties, the measured properties, were very close to the estimated properties. So this shows the genius of Mendeleev's periodic table. But it wasn't complete just yet. The reason it was not complete was because the noble gases were not discovered by then. Only by the end of the 19th century, the noble gases were discovered. They were originally called inert gases, but now we call them noble gases. Helium, neon, argon, krypton, and xenon are all noble gases. Neon must be a common name for you because of the term neon light. It's actually only the red light that is a neon light. If it's blue, it's argon or purple. And helium is a common gas that we use in balloons. Correction to Mendeleev's periodic table came in 1913 by Moseley. Remember, Mendeleev organized the elements by atomic mass, but Moseley did something else. He organized the elements by atomic number. This solved the problem faced by Mendeleev's table, actually, because when listed in the order of atomic mass, the bottom numbers, iodine has a smaller atomic mass than tellurium. So according to Mendeleev's original idea, iodine must come before tellurium. However, when you look at the properties, they must be in the order of tellurium then iodine. So this dilemma was solved by organizing the elements by atomic number. The atomic number of tellurium is 52. Atomic number of iodine is 53. And putting them in the right order, arranging by atomic number, finalized the periodic table and put into the form that we use today. The current version of the periodic table is based on the periodic law, stating that the properties of elements recur in a repeating pattern when arranged according to their increasing atomic number. What does it mean when you look at the periodic table? Elements in the same column have similar properties. For example, group 1A elements have all similar properties. Group 6A elements have their own properties, but they're all similar to each other. The periodic table is made of rows and columns. The rows are called periods that are numbered 1 through 7, and the columns are called groups or families. These are the elements with similar chemical properties. There are two ways to number the groups. In the stock system, the International Union of Pure and Applied Chemistry system, they are numbered 1 through 18 from left to right. In the older system, each group has a number and a letter designation. The letter A designated elements are the main group elements that are numbered 1 through 8, often in Roman numerals. The letter B designation is given to transition elements or transition metals. There are different kinds of elements in nature, and the periodic table does a good job in organizing them in certain places. We have metals. These are substances that have luster and are good conductors of heat and electricity, such as silver. We have nonmetals. These are the elements that do not have luster, and they are poor conductors of heat and electricity, the opposite of metals, such as sulfur. And as a transition between these two types of substances, elements, we have the metalloids, also known as semimetals or semiconductors. These have the characteristics of both metals and nonmetals. There's a staircase-shaped line starting at boron, separating the metals from nonmetals. Elements bordering that line, with the exception of aluminum and palladium, are metalloids. Let's see the parts of the periodic table we have discussed on the periodic table itself. As you see, it is made up of rows and columns. The rows are called periods, numbered 1 through 7. And the groups are numbered in the IUPAC system 1 through 18. These are the top numbers. And the old system divides the periodic table into main group elements and transition metals. Main group elements are the ones in the first 2 columns and the last 6 columns, total of 8. And the ones in the middle are the transition metals. And these are numbered based on the AB grouping system. The lower number shows that numbering, 1A, 2A, and then jumping to the other side, 3A up to 8A. You do not need to worry about the numbering of the transition metals. We also have different element categories as metals, metalloids, and nonmetals. In this colored periodic table, the blue boxes show metallic elements. They are on the left side of the periodic table. The yellow colored elements are nonmetals. They are on the right top side of the periodic table. And in between, we have the green metalloids or semimetals. Do you see the broken line that separates the metals from nonmetals? And the elements adjacent to that line are metalloids, semimetals, with the exception of aluminum and polonium. Even though there are more blue boxes, that means there are more different types of metallic elements than nonmetals, when it comes to the amount, the number of atoms in the universe, nonmetals are by far more abundant than the metals. The most abundant element in the universe is hydrogen. And you might wonder, why is hydrogen over here, even though it's a nonmetal and it's with the metals? It's by convenience, because hydrogen is number 1. It has to be put in the first box. There are certain important groups of elements that you need to know. Remember, groups are the vertical columns in the periodic table. We're going to look at elements of group 1A, 2A, 7A, and 8A. Group 1A elements are called alkali metals. Lithium, sodium, potassium, and so on. These are all very reactive metals. They're never found by themselves in pure form in nature. They're always as part of salts. Group 2A is called alkaline earth metals. They're fairly reactive, similar to alkali metals, but because they're found in the rocks and minerals, they're called alkaline earth metals. Beryllium, magnesium, calcium are some examples. Group 7A are mostly nonmetals, and these are all very reactive elements. They're all toxic to life. And because they're very reactive, they're never found in elemental form. They're always found as parts of salts combined with other elements. For example, sodium and chlorine make sodium chloride, which is table salt that we eat, or which is the salt in the oceans. And the last group is 8A. These are noble gases. They're called noble because they don't like to form compounds with anything else. They're always in monoatomic form by themselves. They're inert and they're non-reactive. So when you look at a periodic table, you should be able to identify whether an element is a metal, non-metal, or metalloid. And then based on its group number, you should be able to determine the type of element it is as alkali metal, alkaline earth metal, and so on and so forth. And remember these properties.